Hello and welcome back to Calculus 3, section 13.5, triple integrals in cylindrical and spherical coordinates.
Are you also going to extend the deadline for the homework?
Yep. So we had snow days and Thanksgiving and Black Friday holiday, and then what's the color for Saturday? And I know there is Cyber Monday and all of that stuff. So yesterday was holiday too? Wow. Okay. I don't know. Cyber Week? Okay, fine. So after all of these things, we are now back. Hopefully we learned some of this stuff now. Cylindrical coordinates. Cylindrical coordinates are built on polar coordinates. So what we have is in XY realm, we have our standard r theta, radius r, maybe I put r above, theta angle, to give me r comma theta point in xy plane. But then I can raise that point z units up, and what I get is r theta z. R theta z, known as cylindrical coordinate, because observe what would happen if the point on the circle is to travel around that circle. If it travels around the circle, then the one on the top would also create a circle and would make a cylinder, right? So these are called cylindrical coordinates. All you do is you have your polar coordinates as the first two coordinates, and then just straight up z, going either up or down depending on what you have, like 3 or -3 and so on. So this is what we have for our cylindrical coordinates. They're very easy, very straightforward, because they build up, they build up directly on polar coordinates. Now, because we have that type of coordinates, we can use the same conversion that we used in the polar world. We know that x was r cosine theta, y was r sine theta, and now we're adding that z equals z. Really not much to it. On the other side, we had that r is equal to square root of x squared plus y squared. That theta was the inverse tangent of y over x. And finally, z equals z. So these were the conversions that we would use to put these, to connect the coordinates that are x, y, z, which is rectangular, to the other side, which is cylindrical. So cylindrical coordinates are simply just add z on top of polar, and we are done. So now, talking about cylindrical coordinates, we have to be very careful, because you have to know if we are talking about cylindrical or polar. Clearly, cylindrical is 3D. Polar is 2D. Because equations are going to look the same, and they are going to mean completely different thing. So, if I have a 2D equation which is polar equation, r equals to 3. This is a circle, right? Radius 3. If I have 3D cylindrical coordinates equation and I say r equals 3, now this now is a cylinder. radius 3. It's a tube. Think of the infinite pipe that it's a radius 3, which is 6 inches diameter, right? So you're thinking of a tube that extends infinitely in a z direction to positive infinity and negative infinity. So it's an infinite pipe, the way I have it here. But what I need to make sure is that you see that you need to know clearly whether we are talking about the 2D equation r equals 3 or a 3D equation r equals 3. So for 2D, it's just a circle radius 3, and that's it. It's a 2D thing. For a 3D, it's going to be the cylinder. Extends infinitely. And then you can have now this is all filled in, right? It's a solid material. It's not hollow like a pipe. If you want to make a pipe, then you will put radius in between two. So this is a cylinder, radius 3, right? And you would draw a cylinder that will infinitely extend in both directions, but it's solid. If you want a pipe, so you want a pipe like this that has a hole inside, right? You would have your cylindrical equation r in between two numbers. Let's say the outer diameter is, I don't know, 3 inches, and the inside diameter is 2 3/4, right, of inches. So 2 3/4. There we go. So this would be a quarter thick wall. Yes?
Isn't R equals 3 a cylinder with a wall with no thickness at 3? If it's less than or equal to 3, then it'd be solid, right?
Oh, yeah, you're right. Not a solid, it's eggshell. Yeah. It's just, you're right. I would have to have less than equal to in order for it to be solid. It is completely empty. It's just, let's call it eggshell wall. No thickness to it. It's infinitely thin wall. Yes, thank you. In order for it to be completely filled in, we would have to have less than equal to 3, like that. To make a pipe, we define outer radius, inner radius, and then the material is right in between. So that will be the pipe.
Is that 2 3/4?
2 3/4, 3/4 for the inner 3/4. There we go. I have to go change the pen because the pen is really dying. It's getting really difficult. Plane z equals some number a. That's standard stuff, right? Cone z equals AR to get the cone, and so on. So now we have to talk about calculus. The stuff we did so far was the pre-calc, right? Define coordinates and see some of the basic shapes. Now it's time for us to define the triple integration so that we can find volume or we can find bulk, right? Because that's what we're looking for. Volume of a cylinder without anything special going on. So volume cylinder. This would be technically your rectangular integral for cylindrical coordinates, and that is numbers all around. Now, what you have to remember here is the string that always stays the way it is. So we have dz, r, dr, d theta. This is the string. Note this r. That's from the polar coordinates r. So now what do we have? Our theta at the end is alpha to beta. Those are angles. Your r is a to b for the radius. And your z is some c to d, or you can put e to f, whatever you want. So now you can see that the bottom of this is c, the top is d, the radius here has the dimensions of a to b, and then if you want the full circle around, 0 to 2 pi, 2 pi for the full, 2 pi for full revolution. So this is volume for a cylinder, you know, which, do we really need the integral for it? No, volume for a cylinder is easy, right? It's the area of the base, pi r squared times the height. You don't need integral in Calc3 for it. But then someone might ask you why, you know, and there you go, that's why. We want to deal with much more interesting shapes, and those interesting shapes will allow us to vary these as functions. And then we also want to put in some function here, density, temperature, something, right? Because the integral will define the object from all sides, right? And then we can integrate something within that object and talk about distributions and accumulations and things like that. So now we're not talking about volume anymore. Oh, by the way, let's just check dimensions real quick. Is z a dimension? Yes, it is. Is r a dimension? Yes, it is. Is dr a dimension? Yes, it is. We already have 3. Is d theta a dimension? No, it's not, right? Angle ones are not dimensions. So we don't get a dimension from there, but we don't need it. We already got 3 for volume, so we're good. Why is angle not a dimension? Because what is the formula for theta in terms of arc length? Very good. So arc length S is measured in, let's say, inches, and radius is measured in inches. So when I cancel those units, what are the units for theta? No units of length, right? Not a dimension. Angle is a ratio, and the units cancel. So that's why angles do not give you dimension in these equations, ever. You only get your dimensions that have units of inches or centimeters or meters or whatever. All right? So that's that part. Now let's talk about the triple integral in cylindrical coordinates. This is the general case. And this is the big equation that we are looking for. So the triple integral d of the function x, y, z dv. So you see dv, you know that's a volume right there, and then times the function here is 4 dimensions. It's given by, and now we need these integrals. I have to convert my f, so x will be r cosine theta. Then I have y, r sine theta. Z is still z. And I have my string dz, r, dr, d theta. That doesn't change. For my triple integrals, I have alpha and beta. For angle, do I want the full circle, 2 pi? Do I want a wedge, 0 to pi over 4? Do I want 1 petal of a rose? Right? Missed opportunity. Wow. I had those cookie cutters. They stayed in the microwave. I could have brought them in. All right. Anyway. We have g of theta and h of theta. These are the functions for r in respect to theta, because r is a function of theta. If you remember anything from your Calc 2 class, chapter 10, you know that r is a function of theta. So here is the middle dr, and here is the middle integral. We see that it's function of theta. And then finally, we have z as a function of theta and r. So the lowercase z is g of r cosine theta, r sine theta, when you convert, and capital H, r cosine theta, r sine theta. Now you're looking at this and you go, huh? And I say, hold on. What do you have? If you have a triple integral with something over here, and then you have your dz, r, dr, d theta, this is your alpha and beta angles. This is your r1 lower, r2 upper, and z1 lower, z2 upper. Now, what is z in terms of? Well, z is in terms of these two guys, right? And look, it is. So it's not that complicated. It looks complicated, but it's not. It's very straightforward. And once you are done with z, you scratch that out, and then you ask yourself, well, what are my limits for r, where r is only in terms of d theta? Well, great. That's what it actually is. G of theta, h of theta. All right, let's put this in perspective by working out some examples. So this is our big formula right here. This pen is cutting out so much now. It's getting really annoying. Anyway, so what do I have? Let's take a look at the problem from homework, and you guys can read the problems that are done in the book, right? You know all the letters and numbers. Good? All right. I suspect that as much your Calc 3, right? Great. I have this half of a cone. I'm not sure if you ever split the ice cream cone this way, but you take the cone, right, you put it up and just cut it right down the middle. So there it is. Half a cone. X, Y, Z. The top is going to be 9. And then this is 3. And this is negative 3 on the negative x-axis. Perfect. It will also extend. This is bad, but it will also extend to 3 this way. Giving away that it's a circle in the base. Do we see x values to be 3 and negative 3, and we see a y value to be a 3? It's a circle. So what is my domain? If I draw my xy domain, I go 1 to negative 3, I go 1 to positive 3, 1 to positive 3, and then draw half a circle. We know what the equation for this is, right? X squared plus y squared equals to 3 squared, which is 9. But then you solve it for y, which is the square root of 9 minus x squared. It's a positive square root. The negative square root is on the bottom, but we don't have a bottom. It's just the top. So if you are looking to set up this integral as rectangular coordinates and solve it, good luck, right? Because it's not as easy and fun to use dx and all of that stuff. But what you can easily do is set up your cylindrical coordinates to find the volume of this object. So what do we have? Well, let's take a look at the triple integral. We are looking for a volume, so there will be no function here. You just have dz, r, dr, d theta string. Don't forget this r. This is 1 unit. You don't break it, you don't change it. That's it. It's like, you know, just drop it down as is. 1 unit together. So let's talk about the limits for our theta. What do you think the limits for theta are? Which is 0 to pi. Thank you. We have to use radian measure. Theta is 0 to pi. We only want a half of the circle. And it is a positive half of the circle, which is the reason why I drew the domain. This is 0, and then swings to pi. The bottom is pi to 2 pi. We don't have that. So it's only 0 to pi for the upper half of the circle that we have in a domain. Great. How about my radius? 0 to 3. Good. 0 to 3, because the radius stretches from the origin all the way to 3 and swings around on the circumference of the circle. Perfect. Now, what do I do for z? Sorry? 0 to 9 would be a straight cylinder. It would be half of the cylinder. I have a cone.
Are you going to make like the equation out of the line, where it crosses the y-axis, where it crosses the x-axis?
We can do that, sure, we can do that. But also, remember what I gave you earlier? Right? So we have a slope, and then we have r as a variable. Slope is -3, so this is -3r. -3r, 0 to -3r. Oh, sorry, y-intercept, 9 minus 3r. There we go. Do we all agree that the slope of this line, m, is equal to -3? Right? You go 9 units up, 3 units over. So 9 units up, 3 units over, and it's falling. That's a -3 slope, right? Do we all see the y, now z-intercept at 9? So it should be, if this was in the xy plane, you would write it y equals -3x plus 9, right? But now, since it's in the polar, we just write it as z equals -3r plus 9, which is 9 minus 3r. Does this bring? Okay, good. So if this makes sense, then we're done. Because now you have 3 Calculus 1 integrals, literally no-brainer, to solve it, right? You do the inner integral dz, which would give you, integrate z, so just give you 9 minus 3r. Now you have times r, dr d theta. You have to integrate this. So 0 to pi, r times 9, 9r, so 9/2 r squared. Minus r squared, so r cubed over 3 and kills the 3. Computed from 0 to 3. Still have d theta. integral 0 to pi. When I plug in 3, that's a 9, that's 81 over 2. Minus 3 cubed, 27. Don't worry about zeros. And then d theta. When you integrate d theta, you will add pi to this mess. So pi, 81 over 2. Minus 27 is a 54 over 2. And the answer is 81 minus, this is 30 minus 3, 27 halves pi. That's all. Fine? Now, the real power of this is when you have a rectangular integral and you just look at it and you say, this is going to be so much trig sub that you just don't want to do it, right? But the beautiful thing with cylindrical and spherical coordinates later is it would convert integrals like that into a joke that you can solve like this. And that's the real power of what we do. So let's say that you have, this is problem 18. Let's say you have integral given as negative 3 to 3, integral 0 to square root of 9 minus x squared, integral 0 to 2 of 1 over 1 plus x squared plus y squared, dz, dy, dx. The problem says integrate. That's it, right? That's the problem, integrate. Okay, z is easy because it would just be 2 over that stuff. And now you have to integrate that in respect to y and plug in that square root thing, and yeah, right? We see where the issues arise. As soon as you get to y integration, hell breaks loose. So what do? We'll convert it to polar coordinates. As soon as you see this beautiful, beautiful and wonderful x square plus y square, as soon as you see 9 minus x squared or 9 minus y squared, guys, that stuff is screaming circles, right? So that is immediate invitation for us to convert this into polar coordinates. Now, conversion to polar coordinates will require of you to draw the picture off of the limits that you are given over there, right? So what you want to focus on are only the first two integrals, because the first two integrals are the last two integrals, which is the domain. This doesn't have to be dz, dy, dx. Remember that, right? This could be in any order. Your domain is always the last two, with the boss being the outer one, in this case x. So I'm not going to draw a 3D picture. I don't care about 3D picture. All I care is about a 2D domain. And if I know what the 2D domain is, that's good enough for me to set up the polar stuff there. Look at the z. It's 0 to 2. That's just going to be flat up rise. So that's cool. So let me focus on drawing this out, right, for these guys. That's all I'm focusing on. So I'm working on the domain of this. So what is my domain? What I see here is, well, I draw xy first. And what I see is a function which says y is equal square root of 9 minus x squared. What is that? That's a circle, right? With a radius 3. All right. But I only have a positive one. It goes from 0. So this is exactly the same like a previous problem. It's lame, I know, but that's what they have in the book. Does this fit? Yeah, it fits. Look at my x. X is from -3 to 3. Perfect. And then from 0, which is flat, to the arch above, half a circle. You see how my dx is perfectly contained there? X is going to move from -3 to 3. The bottom of x writes 0, which is bottom of y, and the top writes the semicircle. Perfect. What is this? This is a half of the cylinder. I don't even need calculus to find the volume for this thing, right? I can do half of base times the height, because this is half of the cylinder. This is literally you taking a can and just cutting it down the middle. That's all it is. It's like the half of the can. But it's a vertical cut, not a horizontal cut. It's a vertical cut on half. Because 0 to 2 is going to raise this base. Guys, this is your floor, XY floor, right? And it's going to raise the base up to 2 inches or 2 feet or 2 meters or 2 miles. I don't care, right? It's raising 2 units up. So all you have is literally half a can that it's 2 units tall, because that's 0 to 2. Now, if it's 0 to a function, it would be something crooked, right? But it's 0 to 2. We know that the flat plane, z equals 0, z equals 2. Well, it's half of the cylinder. So now I have half of the cylinder. And yeah, we can set up our integral because we have to practice. If it was just a volume question, we just do the middle school equation, right? You have your r squared, right? It will be 9 pi times 2 times, and then half. So it's 9 pi. Volume is 9 pi, just by looking at it. But we actually have to integrate because we have that function inside. So now we have to convert all of this, and we have to set up our integral. Great. Let's go. What do I have? First off, I have 1 over 1 plus r squared. That's x squared plus y squared is r squared in a conversion to polar. We have the equation for that, right? You should know that from your Calc 2 class. I wrote it here, that r is equal to square root of x squared plus y squared, which means x squared plus y squared is r squared. That's your Pythagorean theorem. So x squared plus y squared is going to be converted into simply r squared. And then we have the string that we are not to change. R, the R, the Z, R, the R, the theta. Z, well, that doesn't change. That's 0 to 2. Because Z over here is 0 to 2 and Z is Z. So all I need to worry about is the outer one. So what's my theta? It's the same like last time. 0 to pi. And what's my R? Very good. 0 to 3. What kind of joke is this to compute? Right? This 0 to 2 makes it even better. 0, 0, pi, 3. Now when I integrate this in respect to z, I just gain z, and then z becomes 2, right, because 2 minus 0. So this becomes 2 over 1 plus r squared, and then r dr d theta. Do you all see it? What's the integral? Oh, come on. What's the integral? Yes.
Did we just have u subbed it?
Yeah, exactly. U sub. You have r squared in the denominator. You have 2r on top, which is derivative. You can't have easier than this. U equals 1 plus r squared. Du is 2r dr. 0 to pi, 1 over u du, and the limits when you plug in 0 for r are 1, and when you plug in 3 for r, 10. You're not going to bring this back to r. It's a definite integral. No need. Convert your limits. Plug in 0 into r. So 1 plus 0 is 1. And then plug in 3 for r, 3 squared is 9 plus 1 is 10. So solve that. That's going to be ln 10 minus ln 1, which is 0, so who cares? D theta, and then pi ln 10. Yay. 9. ln 10 is a constant. So theta is going to be pi minus 0. So it's just pi ln 10. That's cylindrical coordinates. Now I'm going to ask for one more conversion to practice, and then we're going to move to spherical. So here's another problem. Problem 20 looks nice and evil. I mean nice. That's -4 to 4. Integral from negative square root of 16 minus x squared to 16 minus x squared, and then square root of x squared plus y squared to 4, and then, oh, there's nothing in it, it's just dz, dy, dx. Okay, try this. If you're one of those people that hate themselves, try to solve it without converting. It will produce fair amount of pain. Okay, let's talk about this. What is the domain? Is it part, full? What is it? Full circle. Very good. You have the bottom half of the circle with the negative. You have the upper half with the positive. So it's the full circle. We do see a 16 and a 16 and a 4 and a 4. Perfect. Everything lined up for a full circle of radius 4 for our, there we go. So that's perfect. And Z is a straight up conversion. You don't have to worry about Z. You just convert that to thetas and r's the way it's written. So I need this for a circle, dz, r, dr, d theta. No function inside, which means this will compute volume. And Z conversion is straight up r to 4. Do we all agree that x squared plus y squared will give us r squared, and then the square root will kill the square? So we good there? And then what do we do for a circle? Theta, we want a full circle 0 to 2 pi, and we want the r to go from 0 to 4. We are going from absolute nightmare of the integral into something that you should be solving just by looking at it without writing anything down, right? So it's a very straightforward procedure. Once you know your domain, don't worry about Z, right? Z is a straight up conversion, and we're good to go. Equals to, whoosh, boom, just do it, right? Because we are moving to spherical coordinates. I would suggest YouTube videos on visualizing spherical coordinates. You haven't dealt with this stuff before. Cylindrical coordinates, straight up upgrade on polar. Not as challenging for cylindricals. But sphericals are tricky. Spherical coordinates do have polar in a base, but it has an additional angle. What I found to be confusing for students is the fact that theta is measured the way you are used to be measured, right? Used for angles to be measured, which is from the positive x-axis. And you go counterclockwise, you have positive theta. You go clockwise, you have negative theta. And you have been dealing with that type of measurement since the first time you've seen degrees, right, in grade school sometime. And then pre-calculus 2, obviously, going through all of your math education. But in pre-calc 2, you were also introduced to bearings. You remember how those measured? Exactly. It was measuring from the north or the south. Bearings measured off of the y-axis. So you would say north, 30 degrees east or west, right? So 0 was north. See, now spherical coordinates are that evil. You have x, which is measured the standard way, which is theta, right? And then you have angle phi, which measures the same way as bearings off of z-axis. So that's a little bit tricky thing. You have to pay attention there, all right? So the angle angle phi will measure off of the z-axis, just like bearings measured off of y-axis, you know, pi over 4 east or west, right? Now z-coordinate is going to do the same, z-axis is going to do the same thing for phi angle. So what do we have? We still have good old polar coordinates in your domain. You are going to draw a radius and come up with a certain r and a certain theta from the x-axis. But now we are also going to drop an angle from Z. And that angle is going to be called phi. And then we're going to connect these. And that's going to create, further complications. What's the worst thing about this? The worst thing about this is you actually don't have a set of formulas to do conversions because it's situational. You have to use trigonometry every time. You have to look for triangles and angles. And that is the part that makes this difficult to do conversions unless it's a straight up problem where you see, x squared plus y squared plus z squared and so on. Now, the coordinates here, for whatever reason, only for spherical coordinates, your radius is now rho. It's no longer r. So this point will be rho for the radius. Rho is the Greek letter that actually stands for r in Greek. So rho. And then we have phi, and then we have theta at the end. Rho, phi, theta. Two angles and one length. Rho, phi, theta is the point. And we do have rho squared is equal to x squared plus y squared plus z squared conversion. This is also an equation of a sphere. Hint, spherical coordinates, right? So here's one equation that would do conversions. And then we have these three equations. This is more the reference than memorizing. So rho sine phi cosine theta. When you need this stuff, you look it up. Sine phi sine theta and z equals rho cosine phi. This is the conversion that is needed to go from spherical. Now, guys, no one in their right mind will ever use this. Only if you have, mathematical gymnastics question, right, that has no application whatsoever. Because if you are supposed to compute something that it's in rectangular coordinates, which is x, y, z, you will also set it up in rectangular coordinates. You are all programmed to do coordinates. So you will never actually use this, ever. But it's a good thing to, it exists, it's there. And as I said, you might run into a homework problem, maybe the lab problem, that says convert spherical to rectangular and then compute the integral. Remember that these coordinates do not compete. These coordinates complete each other, right? What is nasty in one system is beautiful and easy in the other system. That's how these systems work. That's why they exist. Otherwise, if one was just bad all the time, we would never bother with it, right? So the one that you actually need is to convert the XYZ realm into the other one. And for that, there are no formulas that are standard formulas. There are, there is the conversion for a sphere plus, good luck with the trig part. But at least the good part is that we still have the list of those shapes that come up. So that always helps. The most basic one being rho equals A, right? In 3D, it's a ball. Right, sphere. Ball. There we go. So rho equals A. So what is rho equals to 5. Rho equals 5 is a beach ball, right? It's a 10-inch diameter. So rho equals A. Very simple. And you know that you can convert that into the square root of these guys. So if they show up, straight up easy conversion. Cone. Cone is so easy. Oh, wow. Phi equals some value, phi 0, or some angle, right? So if you are to say phi equals pi over 6, all I need to do is to draw pi over 6 angle here, which is 30 degrees, another pi over 6 on the other side, boom, cone. This is equation for the cone, but this is equation for the cone in 3D, right? It's gonna give you a straight line if you're in 2D. Again, the same game. Do we have a 2D or we have a 3D equation? If it's a 2D equation, it's just going to give you a straight line on the xy plane, right, going to the origin. But now, since you are in a 3D, it gives you the cone, right? Because it doesn't mention theta anywhere, which means we are taking all of the thetas from negative infinity to positive infinity, but all they do is they just run in a circle like this, creating the cone. Vertical half plane. Theta equals theta 0. It's just a wall that you can swing around. So I'm just going to say vertical half plane. I'll put door. Because think about it, right? What do you have? If you have XYZ over here, and you know that your theta measures from here, so theta 0. If I draw this as a theta 0 and draw the plane, and then I can adjust theta, that's the door, right? So at least now you know equation for the door. Right after this Calc 3 lecture, if nothing else sticks. And you can go to the ice cream place and spill that equation as well. Actually, yeah, you have ice cream right here between these two. Right? It's just one scoop. That's the problem, but it's fine. Do we have anything else? Oh, horizontal plane. The pen is the pen is saying no. I'm done. So horizontal plane. What do I have? I have a plane that it's parallel to the floor, going through the value A on the z-axis. So we have equation rho equals A secant phi. It's important because you are going to have a flat top. If you take half of the ball, right, it's going to have a flat part and then the sphere part, right, or hemisphere. And now the cylinder. Cylinder is rho A cosecant phi. A is the radius of the cylinder. So these shapes would help. All I can is list these. I can't learn them for you. So you'll make a conscious decision one way or another. Now we need to talk integration, and this is where the fun begins. We're going to do volume of the sphere first. So, which way these coordinates work? Radius rho. All right. I managed to mess up my elbow here, so I don't know if I can do it now, but I'll try. So here's what we're going to do. You have your origin 0, 0, 0 right here. You have your z-axis here, and the flat plane over here. If I'm to do this, flat plane xy is the domain. 0, 0 on the bottom, right? So now it stands on the plane, and what I'm going to do first is I'm going to draw the radius rho. So now from here to there is the radius rho on the plane. Then I have my theta, which is going to swing this in the xy plane to create a full circle, which is a disk. Think of it as a literally flat disk circle laying on the plane. So I used up my polar coordinates r and theta, which is, I didn't use the phi in the middle yet. So I have my rho, which is the radius, swing around on the bottom flat to create disk. Then what do? All I need to do is to take that disk and flip it pi, not 2 pi, pi, because half of the disk, right, half of the disk on this side, as I flip this pi, you see what happens with the half of the disk? The half of the disk will trace the upper half of the ball. The second half of the disk is going to make the bottom part of the ball. That's why you only swing pi, not 2 pi. You swing theta 2 pi to create the full disk. And then all you need to do is to swing pi, right? Like flipping a pancake, right? Boom. It is going to create a full sphere. So if I am writing the basic integral for volume of a sphere, I have triple integral. Now, string, you have to memorize. Rho squared sine phi, right? So that's the rho squared sine phi, the rho d phi d theta. The rho d phi d theta. This is a unit. You don't break it, you don't change it, that's it. You just dump the whole thing on a page. Anytime you need spherical coordinates, it comes out as a unit. You are memorizing that string as is. If you're interested in derivation, it's in the book. You can talk to me as well, but yeah. What do I have for the volume of the sphere? We said theta is going to draw my domain 0 to 2 pi. My radius is 0 to whatever the radius is, so I'll just put 0 to capital R or lowercase r, whatever. That's the radius. And the middle one, I said we only swing pi. This is equal to 4/3 pi r cubed. You don't believe me? Well, you'll do this exercise at home. This is also honors question for the exam, possible honors question for the exam. the entire calculation, not just, you know, you're writing it to me like, oh yeah, you can work it out at home. Doesn't fly. So here is the just do it. This is just do it for all of you to show. It's a great conversation starter, right? You meet someone, hi, my name is Joe. Oh, by the way, do you know that you can prove the volume of the formula? And write this integral immediately. It does wonders, trust me. I have tried it in the past. But you know what? The volume of the sphere is not the reason why we all gathered here today in such a large number. We have, yeah, we're only missing 4. That's okay. 1, 2, 3, 4. Yeah. Tell him I forgot how it looks, what it looks like. Okay, like, yeah, it's like, and the club friend over there, too. What do we want to compute? We want to compute again the same thing, right? The volume or the bulk, having the triple integral spherical coordinates. So what I want to do is I want to take a look at the triple integral over region D for f of rho phi theta dv. Now I need a lot of space, which is why I'm doing this in 2 lines. So now I have my triple integral f of rho phi theta, and guys, I have the string rho squared sine phi d rho d phi d theta. Theta is standard alpha to beta. That's the domain, right? Now phi is going to be a to b. This is the easy version, and then the we have g and h over here as a function of phi and theta. These are the outer. So this is the spherical coordinates integral light version. The worst one is not a part of this, obviously. It has the functions on all parts. So, all right. Let's take a look at a problem. Again, if you're able to set these things up, the rest is not a problem. Okay, great. Why simple if we can complicate things, right? Mathematical gymnastics. We all know the volume for the cone, right? 1/3 base, which is a circle, times height. Very simple. But let's say you don't want to do that. You like pain. So you are deciding to do this in spherical coordinates, as you would. So this is what we have in problem 42. And they nicely gave you this pi over 3 angle over here. Usually you have just a measurement and you have to come up with that angle using trig. Remember what I said, the conversion? You would have trig that this side is 4, radius on top is blah. You can do the tangent thing and figure out the angle, right? But, you know, the author of the book is a very nice person and just says, yeah, don't worry about the tangent over there. You have your pi over 3, go, right? You have a choice to do grade school formula, to do cylindrical integral, and now to do spherical. Well, we're going to do spherical because we can, right? So what is in my base? Well, it's always polar coordinates, r theta, in this case, rho theta. So to find the volume, I have my triple integral, and I have my string, which is rho squared sine phi d rho d phi d theta. That's a standard string. That doesn't change. Is this a full cone? Yes, it is. 0 to 2 pi. Now, here's the $1 million thing. What is the phi, the inner integral? What is the phi? What are the limits? Well, 0, 2 pi over 3. Very good. You have to get used to, speak of the devil, look at that. Oh, and it says bye, and then he walks away. Did you just text him? You did? Nice. All right. I know you exist. That's good. I mean, anyway. So, 0 to pi over 3, because 0, good effort. 0 is at the z-axis, right? Remember that 0 is always that. And then we fall off pi over 3, which is 60 degrees. And then we let it swing at pi over 3. It creates the cone. Which leaves us with a rho. Now, what's rho? Please note that at this peak, what's the radius at this peak right there? 0, right? And it extends to what up there? To the? What is the top? What does top looks like? What does the top look like? Yeah, but what is that on? It's on the flat surface, horizontal plane, a secant phi. So 4 secant phi. There you go. See? Nothing you can't take care of. Bueno? Yes, you will learn that the horizontal plane is a secant phi because you have to. That's what you're learning in Calc 3. Integrating this, guys, is all Calc 1 basic integration, right? Why are no formulas given in Calculus 3? Because formulas is all you learn. You're not learning new integration technique. You better be able to integrate the rho square and get rho cubed over 3. You've been doing that for over a year now. Calc 1, Calc 2, right? So no one is going to be ecstatic that you can integrate rho cubed. Your job is to learn that the flat plane in the cylindrical and spherical coordinates is rho equals a secant phi. That is what you're learning in Calc 3. Now the integration is Calc 1, so that, go. So we have the rho integral first. Sine phi is a constant, so don't worry about it, just copy it. We have integral 0, 0, 2 pi, pi over 3, rho cubed over 3, sine phi, and then 0 to 4 secant phi. We still have d phi, d theta to deal with. You will plug in your secant phi into rho, get secant cubed phi. So, double integral in front. I'm thinking if I should, waste time solving this, or I should do another example. So now we have 4 cubed is 64 divided by 3 secant cubed phi sine phi d theta. Hello, Calc 2. This is a trig integral, section 7.3. This is where you put that, little note in your notes. 7.3. You are supposed to solve this. Now, are secant sine pair for integration or derivatives? Are there trig pairing? No. What are the trig pairs? What's the ratio of sine? So sine, cosine is a pair. What's the ratio of secant? Secant, tangent. So secant, tangent are a pair. And what's the cosecant is? Cosecant, cotangent. So that's a pair. So sine, cosine are a pair. Secant, sine is not a pair. So we have to convert something and work within those limitations. So what do I convert? I convert secant into 1 over cosine cubed. And then I have my sine, cosine pairing. Cosine cube is in denominator, so it's an easy and cheap U sub. Good. So we don't have to use any heavy weapons over here. It's just 64 over 3. Can kick that in front if you want. This becomes sine phi over cosine cubed phi, d theta, here in blue, U equals cosine cubed phi, no, sorry, cosine phi, du equals negative sine phi d phi. And there you go. 0 to 2 pi, 0 to pi. No. We have to convert this. Cosine of 0 is 1. Right? Converting limits. Cosine of 0 is 1. And cosine of pi over 3 is 1/2. Now you're going to say, well, 1 is bigger, it's on the bottom. Yeah, but you will also get the minus sign. And then you can lose that minus sign by flipping these. So, yeah. 64 over 3, negative 1 divided by u cubed, du d theta. So this was another u substitution within the triple integral. So it's nice. I'm going to get rid of the negative. So let me actually write that here, orange. Negative will flip the limits. This is the formula that I will be teaching. No, I already taught it. In my Calc 1 class, 5.2, for definite integrals, if you swap the limits, you pick up a minus in front of the integral. Well, that minus 1 will swap those to half on the bottom and 1 on the top. So I have 0 to 2 pi, 64 over 3. I'm integrating u to the negative 3, so plus 1 becomes u to the negative 2 over negative 2, right? So this is 1, or you can put negative 1 again, over u squared, now from 1/2 to 1. We picked up another negative because of the integration. D theta. I got bored. There we go. Next problem. It's better time investment. Plug in 1 and 1/2 and then just times 2 pi at the end. I didn't last too long. I'm sorry. These two problems are solved. Okay, let's do it. So we have another cone that it's not going to be a full cone hitting the origin. This cone is going to have a scoop taken out of it from the bottom. It's going to have a flat top at 2. The bottom of the cone is going to be scooped out. So you're going to have a cone that when you look from a side, it just looks like a cone that it's cut off. But if you look at the bottom cut off, you will see that there is a scoop, a spherical scoop taken out. So what do we have? We have the flat top. This is too long. flat top at 2. And then I'm going to make these at these not supposed to be at 45. And then the bottom is like this. But here at 1, there is a scooped part inside that you can't see. And then your x and your y axis and your z. That's a 2. So top is flat. We know that that's going to be given as a rho equals a secant phi, right? The bottom is a ball, sphere, rho equals 1. Because there will be a ball over here of radius 1 that fits, and that's what's scooped out, the bottom. And I already said that the angle over here is pi over 4, which you would actually have to figure out if you're given measurements. If I was to put one of these shapes and things on the project, you would have to measure, and then you would have to figure out the angle pi over 3, pi over 6, or whatever. 17 degrees, you convert that to radians, whatever it is. And they want to compute this for the function rho cubed. So they're not looking for volume. They're looking for 4D, because you are supposed to compute, oh sorry, it's 1 over rho cubed. F is equal 1 over rho cubed. All right, so I have my triple integral. 1 over rho cubed is a function that I'm supposed to compute. And then I have the string of rho squared sine phi d rho d phi d theta. Standard string. Remember, you are just dropping this on the problem. That's it. 1 unit. And now we have to deal with limits. Theta. I said theta.
Oh, 0 to 2 pi.
0 to 2 pi is the full circle. It's the entire cone. If I cut half of it, then it's 0 to pi. If I want the other half, it's pi to 2 pi, right? If I want a wedge from pi over 4 to pi over 2, right? It's a quarter wedge. It will be right here somewhere, right? So I want the full thing, and that is, oh, okay. If it's an issue for you guys, you know what we do. We shine the light from the top. It creates my domain on the bottom. Is my domain full circle? Yes, it is. 0 to 2 pi for theta, right? Whatever helps, just make sure you are able to see that. What's my phi? And 0 and pi over 4. Because, again, 0 at z, drop down pi over 4, let it rotate 2 pi around, it's creating a cone. Green? You need to do these things. You need to do these things when you go home and figure it out, right? And it's also a good thing to, you know, kind of get your elbows, do some exercise and so on. So, 0, drop down pi over 4, do the full circle at pi over 4, you see the cone created in front of your eyes. And also I did suggest, right, the visualization YouTube videos for spherical coordinates. You gotta see these things, they have some awesome animations there. So visualize spherical coordinates, YouTube, look for those videos, absolutely amazing stuff. What's my rho? 1 on the bottom, very good. The bottom is scooped out by a sphere 1, so that's the bottom. What's the top? 2 secant phi. Thank you. Look at those rows canceling. You have to integrate 1 over rho, which is ln. Great. And then you will have ln of secant phi, and yeah, it's going to be wonderful for you to integrate these things. This is where I check out and I say bye. Good luck. Here. That's it.
Is that a G hour?
Yeah. Good luck, have fun. That's that's what you at the start of every competitive match you want to look nice, right? Even though you're not. You're just a troll no one likes. Anyway, all right guys. See you in 2 days if there is no snow or apocalypse or a holiday or something.